This small lecture is based on the second principle of mathematical induction. In the previous lecture, we were talking about the first principle of mathematical induction. So, this is a more strong principle. In what way it is stronger? That would be seen now. The second principle of mathematical induction. I want you to recollect a mathematical induction procedure comprises of the basis step as well as the inductive step. It can be used only for known result. You cannot prove a new result using this technique. You can only verify. Okay. So the second principle of mathematical induction. This is also called the strong principle of induction. This is also called the strong principle of induction. Given a mathematical statement S of n, given a mathematical statement S of n that involves one or more that involves one or more occurrences of the positive integer n and if number 1 s of 1 is true, that is your basis, and if s of 1 s of 2 etc, s of 1 s of 2 etc, s of k, s of 1 s of 2 etc, s of k are 2, s of k plus 1 is also true. Then we conclude S of n is true, S of n is true for all n in Z plus set of positive integers. Okay. Now the first step is called the basis step. The second step is called as the inductive step. I suppose by now everybody would become familiar with this. We don't have to keep repeating this. Now some problems based on the second principle or the strong principle of induction. State and prove fundamental theorem of arithmetic. Your first problem, state and prove the fundamental theorem of arithmetic. Right. What is the statement? This you would have already learned in your unit 1 or unit 2, I suppose. So the statement is every positive integer n which is greater than or equal to 2 is is either a prime or product of primes. It's either a prime or can be written as a product of primes. All right. How are we going to establish this result? So we have to prove this P of n statement is true for every n greater than equal to 2. So to prove P of n is true for every n greater than or equal to 2. For this, we have to start with basis step value taken to be as 2. So your basis step, we have n naught equal to 2. Here I can write my P of 2. I have to write it as a product of prime. 2 is the smallest prime number. So it's equal to 2, which is a prime. Hence, basis is true. Okay. A single number can be thought of as a product because 2 could be written as 1 into 2, obviously. Next, inductive step. We assume the proposition is true. We assume the proposition is true for all integers up to k. For all integers up to k, where k is strictly greater than 2. That is, we go for p of 3, p of 4, so on up to p of k. Everything is going to be true. Now we have to prove p of k plus 1 is true. Now we need to prove p of k plus 1 is true. Okay. So how to prove p of k plus 1 is true? If it is a prime number, we are through. Otherwise, so if k plus 1 is a prime number, then there is nothing to prove. We are through. If it is not a prime number, then what happens? It is a composite number. So it can be factorized. So it is not a prime number, then it is a composite number. So it could be written as product of two positive integers. So could be written as a product of two positive integers, say x and y. So 1 is strictly less than x comma y, which is again strictly less than k plus 1. Since x and y are less than equal to k, they can be once again factorized by our induction. So by our induction hypothesis, they are product of primes. X and y are primes or a product of primes. That means what? Either they are either prime or a product of primes. So now let us start. How can we replace this value? X could be rewritten as some p1 power, let me say p1 power some r1, p2 power r2, etc. Some pl power rl. Similarly, y could be written as some p1 power q1, p2 power q2. These are all integers with the prime numbers raised, etc. ps power qm, something like that. So when you multiply x and y, they are again going to be a product of primes. That is what can I say? My P of k plus 1. So I have now my k plus 1 is nothing but x into y. This is a product of two or more primes. This is a product of two or more primes. Therefore, therefore, P of k plus 1 is true. So, by mathematical induction, by mathematical induction, the theorem is true. The theorem is true for all n greater than equal to 2. Let us now consider some maybe simple example we can consider. See, suppose I take a number like 120. I start factorizing by 2. I will get 60. Again by 2. I will get 30. Again by 2. I will get 15. By 5. I will get 3. Again by 3 I will get 1. Okay, I'll just factorize this. Okay, so now in general, now consider this 120, I have to write it as a product. How can I write this as a product? I can write this as 5 will go in this 3 times, 3 will go in this, so I can write this as 15 into 8. Correct? I can write this as 15 into 8. See, one way I can write this, I can write this as 15 into 8. So 15 into 8 is 3 power 1 into 5 power 1 into, see, this could be taken like my x. My y could be 2 cube. This could be taken as my y. So this is a small illustration whereby you can see. Here it is repeated, your L1, M1 and all, this is what it is telling. 2 raised to the power how many times? That is what is represented. Okay, I hope you understand. Next, use mathematical induction. MI denotes mathematical induction to prove that A minus B is a factor of A power n minus B power n for all positive integers n. For all positive integers n. Okay, solution. So let P of n denotes, let P of n denote A minus B is a factor of A power n minus B power n. Now I have to prove P of n is true for every n greater than or equal to 1 because positive integer 1 is included. So for my basis step, my n naught should be what? Should be 1. So n naught equal to 1. What can I say? My a power n minus b power n is a power 1 minus b power 1, which is a minus b. So clearly a minus b is a factor of p of 1. Therefore, my basis condition is satisfied or my basis is true. Next, consider for n not equal to 2. What is your n not equal to 2? I will have a power 2 minus b power 2. This is again a plus b into a minus a plus b into a minus b. Therefore, a minus b is a factor, correct? Of a squared minus b squared. Hence, P of 2 is also true. Now, inductive step. Assume the result is true for k. assume the proposition is true, assume the proposition is true for all integers up to k. That is, I have tried for 1 and 2. I want to try for k greater than equal to 3. Now, what I have to prove? I have to prove p of k plus 1 is also true. This is what I need to show. So I have to consider a power k plus 1 minus b power k plus 1. So what I try to do is, I try to rewrite this as a plus b into this value and try to see how I can rewrite this. Let me just try. How can I write my a power k plus 1 minus b power k plus 1? I want to write it as, let me just try, a plus b into a power k minus b power k. Now what happens? I have a power k plus 1. I have minus a b power k, which is not there. So add that quantity plus a b power k. Similarly, I have a b a power k, which I am not having in the left hand side. So subtract b a power k. Once you do this, try to rewrite this. How can I rewrite this? I can rewrite this as a power k plus 1 minus b power k plus 1 is a plus b into a power k minus b power k plus ab power k minus ba power k. So this is a plus b into a power k minus b power k plus pull an ab common b power k minus 1 minus a power k minus 1. This is nothing but a plus b into a power k minus b power k minus, I can rewrite this as ab, pull the negativity outside, I'll have a power k minus 1 minus b power k minus 1. Okay, so this, in other words, what do I know? The result is true up to k. So since the result is true up to k, I can say that a power k minus b power k can be written as a power k minus b power k can be written as what? A minus b into some value. So I can say something like a minus b into some x. Similarly, a power k minus 1 minus b power k minus 1 could also be written as a minus b into some value y. Therefore, a power k plus 1 minus b power k plus 1 will be equal to a plus b into some a minus b into x minus ab into a minus b into y. So this is a minus b is a common term, x into a plus b minus a b y. Therefore, clearly my p of k plus 1 is divisible by a minus b. Hence, what can I say? P of k plus 1 is true. Therefore, by mathematical induction, the result is true. By mathematical induction, the result is true. This problem carries some importance. So we will do another sum by giving specific values to your A and your B. Okay. So prove that 8 power n minus 3 power n is a multiple of a minus b. What is a minus b? 8 minus 3. So it is a multiple of 5 using our mathematical induction. So let us take the given thing to be p of n. So proposition, let the given proposition be P of n. Now come for the basis step. I have to start from n is equal to 1. Okay, for n greater than equal to 1. So when n equal to 1, 8 power 1 minus 3 power 1 equal to 5 is divisible by 5. We are done. This is my P of 1. So when n equal to 2, my P of 2 equal to 8 power 2 minus 3 power 2, 64. 8 squares are 64. 3 square is 9. So it is 55. So 55 is also divisible by 5. So P of 1 is true. P of 2 is also true. Then inductive step. So we assume P of k is true. So my 8 power k minus 3 power k is divisible by 5. So let me write it as it is 5 times m, where m is a positive integer. Now I have to show P of k plus 1. So consider 8 power k plus 1 minus 3 to the power of k plus 1. How can I write this? This is 8 into 8 power k minus 3 into 3 power k. Split this 8. 8 could be written as 3 plus 5 into 8 power k. You are splitting it as 3 plus 5 because you have to show it as a multiple of 5. Okay. So minus 3 into 3 power k. So this is 3 into 8 power k minus 3 power k, combined terms containing 3, plus I have 5 into 8 power k. But what I know, let us take this as equation 1. 8 power k minus 3 power k is 5m. So this is 3 into 5m plus 5 into 8 power k from the first equation, equation number 1. So 5 could be taken common. So it is 3m plus 8 power k. Therefore, P of k plus 1 is divisible by 5. This is what you have to show. Hence, by mathematical induction, the result is true. See, everywhere we have shown P of 1, P of 2, and then we go to the inductive step, showing that we are adhering to the second principle of mathematical induction. Okay, I suppose these are the two main problems of concern. When we come here, with this, we come to the end of mathematical induction.